Fantastic. Thank you very much for the kind introduction. Right, yeah, so I'm here on behalf of Niels Wedi, who planned to give this presentation originally and who is otherwise indispensably occupied today. So it gives me the opportunity to speak here. Right, like Andy said already, I'm talking about Destination Earth today, and in particular about some of the opportunities and much more the challenges that we face in implementing these digital twins on the HPC systems. So Destination Earth overall is concerned with the delivery of a digital twin of the Earth system, and this is mostly motivated by the fact that we can now run such high resolutions and achieve a level of fidelity in Earth system modeling that we approach a level where you can't really tell anymore from a visual inspection whether this is actually a photograph or a model output. And this is a very, very exciting step change, not only for the overall community, but scientists are obviously very excited about this and the opportunities this yields. And we as technical people are also very interested in this because it presents us with many challenges in mapping this efficiently to the underlying compute hardware. So Destination Earth is an initiative by the European Union with the one sentence summary of towards a digital twin Earth. The EU has entrusted 3 entities with its implementation. That's ECMWF, the ESA, and EUMETSAT, with distinct separate responsibilities. And ECMWF is in this context responsible for the delivery of 3 core components in the first phase of this initiative. So this is the first one is the so-called digital twin engine, which encompasses something like a common approach for orchestrating Earth system simulations and how they can be fused with observations and to enable dealing with the large-scale HPC and data handling resources that are required for these kind of simulations. The second and third point are basically digital twins that then are built on top of this digital twin engine. And the first 2 high priority twins there are one that is triggered on weather-induced and geophysical extremes, and the second one that is mostly concerned with climate change adaptation. I'm not going to talk about the climate change twin today. This is contracted out, and it hasn't been announced yet what consortium is going to work on this. I'm focusing on the extremes digital twin today, and this mostly consists of 2 different components. So one is a continuous digital twin, which is a global model based on ECMW's integrated forecasting system, IFS. And a second component is a hyper high resolution regional model that is then basically a subsequent forecast step on top of the continuous digital twin, continuous global digital twin. And this hyper high limited area forecast model is also implemented by a consortium that is led by Météo France. Let me quickly say a few words about this digital twin engine first. So this is a kind of framework that is envisaged to provide the workflows required for working with digital twins for Earth systems. So this encompasses mostly HPC adaptation and optimization tools, provides ways of working with the I/O and data requirements, and the overall software management, control workflows, and also includes aspects of exploring cloud environments, containerization, and after all, visualization, of course. So in a sense, you can think of this as something similar to a game engine, where a development studio would build on top of an existing game engine their implementation of a game. but in this case, it would be for Earth systems. So it is a collection of APIs and services, and each of these components can, but must not be, but you don't have to use them. It's basically an opt-in portfolio of things that can help you in implementing a digital twin. So the initial list for things that we may see in the first phase are concerned with the overall workflow management, but also with individual components inside the workflow, such as the data structures and parallelization of the models, a plugin architecture is envisaged for downstream processing of forecast outputs while running the actual forecast. This, of course, then plugs in with machine learning and AI applications. And then a lot for I/O processing to handle this massive amount of data that is expected to be generated by these kind of forecasts, and ways on post-processing this, notifying the data storage frameworks behind this, and working with the data overall. The way this is planned to be run is, so I should have mentioned on the overview page, we're working in very close collaboration with the centers that run systems on behalf of the EuroHPC network, and we've heard about the 3 biggest ones this morning, and the plan is to have these digital twins run on this hardware as efficient as possible, and then have as part of this digital twin engine, the necessary infrastructure to lead out the data to the data lakes and make it available to users downstream. But what I want to, so I don't think I need to say any more about EuroHPC at this stage. What I want to focus on now is really the model adaptation of IFS to these EuroHPC systems, and the kind of challenges we face there, and our overall adaptation strategy that we follow there. So this is closely linked to the general HPC accelerator adaptation strategy that we have at ECMWF, and which is tracked internally in a project called Hybrid 2024, and this is led by Michael Lange. And it mostly consists of 4 principles. So the first one is that we establish a mechanism to routinely deploy benchmarks and evaluate the performance across a wide array of architectures and target systems. The second one is that we use, as much as possible, libraries and individual components in separate modules to make it easier to port them individually, and then compose the overall hybrid model from these individual components. An important aspect in there is a flexible management of arrays and the field data, to make it transparent to scientists writing the scientific algorithms under the hood, from the intrinsics of handling the data placement and data allocation and data transfers, for example, between host and GPU accelerator devices. And last component is source-to-source translation. This is something we develop and apply in particular for code parts that are changed and developed frequently. And the idea is here to enable the technical challenges in porting to the target architectures without hindering scientific development in parallel, and to basically have both of them progress in parallel, and always work on basically the latest version of the model with the technical adaptation as well. So quickly about the routine benchmark deployment. So of course, forecast experiments and forecast runs are run both routinely as part of the operational workflows, but also as part of the research workflows at ECMWF. And we have a very sophisticated way of dispatching these experiments, setting up the initial conditions, evaluating the results, etc. However, this is very much dependent on the infrastructure that we have in-house. And so one of the first things we really had to work on is actually make this more portable and find a way how we can run these kind of forecast experiments on across a wide range of machines in the same way as it's done in-house, but without the necessary infrastructure present. And so this range is, of course, across along the typical pipeline of steps that you have to go through when you run any kind of physical simulation, really, from generating and transferring the initial conditions to a portable launch mechanism to actually initiate the simulation that is capable of working on across different submission systems, across different kind of hardwares, and that also enables you interactive workflows, which is absolutely crucial for debugging. And then some kind of result validation mechanism, which allows you to actually check if your outcome is correct. And of course, what we are ultimately interested in is the performance that we achieve. And so we have a mechanism of collecting performance metrics and track the evolution over time. For many of these things, we can actually build on prior experience from, for example, the RUPS benchmark, which is a particular version of IFS tailored towards running as a benchmark across different hardware. But this hasn't been really integrated with day-to-day research workflows. And so, for example, it wasn't possible in the past to run an up-to-date development branch of IFS just on a different machine, and this is something very much being worked on, and where we benefit from the experience that we already have, for example, from large-scale, high-resolution projects like NextGEMS and Insight, but also from the general use and deployment of RUPS in the past. And one important aspect is this is also being integrated into CI testing to make sure that going forward, whenever there are developments on the master branch of IFS, that this will not break our assumptions about porting to different architectures and do not degrade performance levels that we have achieved already. Then the second component of this is to find a way of abstracting the memory layout and the memory placement for data arrays from their use in scientific compute routines. This is a challenge that's being posed on the hybrid nature of GPU accelerated systems, where you always have to deal with the shuffling back and forth of data from host to offload device and back, depending on where you need it. And so this is basically built with two components. One is a so-called field API, which is essentially just object-oriented data structures that allow us to encapsulate the memory placement of the field arrays that we use in IFS, and therefore enable to some degree a separation of concerns. The management of the data allocation and the management of the data offloading to accelerators from their actual use inside scientific routines. And a backend for this, to some degree sense, is envisaged to be Atlas, the C++ library being developed at ECMWF for many years now, with the intention to provide data structures and common algorithms for numerical methods in the weather prediction and climate modeling community. And the Atlas provides function spaces, meshes, grids, and partitioning methods for this, interpolation methods for this. And all of this becomes increasingly accelerator aware, and thus is an ideal fit to basically form the backend of such an object-oriented field API for the encapsulation of the memory layout, memory placement strategies. Third component actually already are the libraries and standalone components. So a lot of work has been put in and is continuously being put into increasing the modularity and the composable structure of the overall code base. This is important because this allows us to encapsulate individual components without having to wonder about the rest, and thus enabling us to port these individual components on a much better to handle code base, smaller code base, individual benchmark tests for these individual components without the hassle of working with the full forecast model. So two examples. The ECTrans library is the spectral transforms library used in IFS. IFS uses a spectral transform method, which requires in every time step to transform the grid point data into a spectral space, where then horizontal derivatives, for example, are trivially computed, and then transform this back into a grid point space where grid point computations are carried out. And this is a rather costly component of the overall forecast. And so this was a natural starting point for any GPU offloading developments, because it's a relatively compact code base compared to the rest of IFS. It has a very clear interface with the rest of the code, and it ultimately enabled us to provide CPU and GPU enabled code paths behind a common interface and thus basically abstracting the hardware details from the use of the spectral transforms. The second component is Cloud-C, which is a standalone dwarf that was created in the ESCAPE project, and which allows us to assess single node performance quite well, and is quite representative of the overall physical parameterizations, which we use as a proxy to develop basically the offloading capabilities there. So I'm running out of time, so let me just quickly highlight some of the results. The first is a rather busy plot, but basically ECTrans tested across a wide range of architectures with the current operational configuration TCO 1279, which shows rather good scaling behavior. The red graphs are our operational or our soon operational ATOS machine based on AMD Rome, and compared to, for example, the A100s in the Joules booster system, or even A64FX nodes. The second one is Cloud-C, which we have tried on a wide range of architectures, and where we can see really good speed up from porting on GPUs. So on the left, we see a few different variants of this dwarf that have been generated via source-to-source translation, or subsequent hand porting based on this source-to-source translated versions. And compared to for example, again, Milan and Rome chips on CPU, we can actually expect a reasonable performance improvements from using GPUs there. The MI250 numbers are very preliminary, so please don't interpret them in any way. It is basically there to show that we have managed to run on there now as well, but we have no time spent whatsoever yet on optimizing for that architecture. And lastly, I won't go through everything there, but basically, especially the physical parameterizations are very large code base, and adapting and frequently changed by scientists. So this is where we use source-to-source translation to apply recipes of how to port and change loop and data layout to make it optimal for the target architecture. And this is very much based on our in-house source-to-source translation tool, Loki, which is applied at build time and thus acts essentially just like a complex preprocessor step in the overall compilation toolchain. Yes, with this, I'll close and would love to answer any questions you might have.